now let's go towards this, let's get a little bit more specific. Okay. So all the good nice pictures are done, finally we have to come back to Maxwell's equations, right. Right. So we are going to make some simple assumptions. We are going to assume single frequency e to the j omega t, and we will make the problem 2D, and we will take a single polarization Ez. Ez corresponds to which polarization? Tm, right? Tm polarization. Yeah. Ez, Hx, Hy. So much of this is going to be familiar to you all because we are going to use a volume integral method, right. That is the most easiest and most intuitive way to formulate this inverse imaging problem. Okay. So this is volume integral. First equation, well, okay, so here are your Maxwell's equations, curl of E, curl of H, and I have put a J term over here. What do you do next? Start. So this is a revision for you all for volume integral. I want to eliminate one variable. So what do? Take a curl of the first equation, right, and play around with a little bit. Divergence of E is 0 in a 2D problem over here. So I get a wave equation, right. We are familiar with all of this. Then we specialize this in two different cases, right, with object, without object. So with object is equation 4 and without object is equation 3. What is the difference between these two cases? The current source is there in both cases, with and without object. The only difference is the object's presence came to be known due to permittivity term. That is the only difference, right. Any other difference you can think of? Of course, the electric fields are different, they had better be different. Mu can also be different, yeah, mu can also be different, but I mean unless you are trying to image some magnetic medium, which is usually like the human body is not a magnetic medium, right. So over there mu r is 1, so that complication we need not worry about. Yeah, so the only difference is electric field changes from incident to total. That is one change, and the second change is I have permittivity as a function of space, right. We have already seen this. What you do is you subtract these two equations and I want to keep the left hand side to have only k naught squared. I do not want this epsilon r term on the left hand side, and we will come to why. Then I have no choice but to move the epsilon r term to the right hand side. So this is a familiar equation to us by now. Okay. There is, so you will notice now in everything that follows, this epsilon r minus 1, this is what appears in every equation, will appear in every equation because it always comes as one term together. So it becomes a little cumbersome to every time write epsilon r minus 1, epsilon r minus 1. So what do I do is I define a new variable, I call it contrast, and that contrast is simply this epsilon r minus 1. Okay. So there's nothing new about it, it's just a convenient way to hold that and make the right hand side look little bit more compact. Fine, familiar to everyone? Right. So I have just rewritten that same equation now. I have the contrast term over here on the right hand side, right. And actually at this point we can make a distinction between forward problems and inverse problems. We already knew this intuitively, but forward problem looking at this equation is what? Give me Ei and epsilon r, right, and as a result obtain electric field everywhere. That is what the forward problem was, which is what we did in the volume integral formulation, right. We assume that, for example, the permittivity of an aircraft, that was given to you. That is the forward problem. Now inverse problem looking at this equation is you are going to be given the electric field. So if I give you incident field and scattered field, from that you can get total field, right. So E is given to you, E incident is also given to you because you have designed the transmitting antenna, right, and you want to obtain permittivity everywhere. Okay. So this is just a revision of what you already know in a little bit more formal way. And this is a real challenge of this problem. The forward problem gives me unique solutions, and the inverse problem on the other hand has infinite solutions, and we will see mathematically why there are infinite solutions. So, imagine why this is a challenging problem. You have infinite possible values of epsilon r which are giving you the same scattered field. That is what infinite solutions means. That means there are infinite possible configurations of the tissue which can conspire to give you the same scattered field. So, how do you know which one is the correct one? Actually, you do not know. So, you have to make a very good engineering guess about which one to choose, which is why this problem becomes a very good mix of not just electromagnetics, but also signal processing. Okay? Because just electromagnetics alone, you get infinite solutions, you can't solve it any further. Okay. So, let us see. So, coming back to this equation, we know how to solve this, right, and that is using the theory of Green's functions, right. So, Green's functions, that is why I needed this k naught squared over here. So, this equation and this equation, both of these equations, the form of the operator is the same, right. So, should I write it again? Yeah. The form of the operator is the same. What is the form of the operator? Del square plus k naught squared, right. What is different is here the right hand side is something and here the right hand side is delta function. And how did we solve this equation? Yeah, but how did we arrive at that? We took the impulse, we took this Green's function definition, we multiplied this by what? The right hand side of the first equation and integrated it over r prime, right, and this equation 2 became exactly the solution to equation 1, and that is written over here, the solution, right. So, it is the convolution of this Green's function which we have spent a lot of time studying in a module on Green's function, convolved with whatever was on the right hand side. So, what was on the right hand side? Chi r E r, that chi r E r is appearing over here, k naught squared has come out, and what is all of this equal to? E minus E I, right. So, in this equation now you can appreciate the forward problem. Epsilon r is given to you, that means chi r is known, Green's function we have calculated. So, this is an integral equation, my unknown is both inside the equation and outside the equation, right. So, I solve for E given this, right. Now that, so while that is clear, let us go further. This is how we had solved this integral equation. As I mentioned, the unknown is both outside and inside the integral. So, what did we do? We took our domain and we discretized it into little squares. In a 2D problem squares, in a 3D problem cubes, right. And the simplest way to solve this was using what is called a pulse basis function. So, what is a pulse basis? 1 inside a little square, 0 everywhere else out, right. So, you have all done this and solved this for your in your assignments, and I write this electric field now as a summation over all of these pulse basis functions P and R, each of them having an unknown weight un, right. So, uns are the unknowns. Earlier the field was unknown, now my unknown is a bunch of scalars un. Will these uns be real or complex valued? In general, complex valued, right. Your Pn is of course real valued pulse function, is just 1 or 0, but un can be complex. And then how did we solve it? We made this r vector cycle over each one of these points one by one. So, when I take r to be one point, I get one long equation in n variables. What is the thing to be taken care of over there? When I am solving this equation, I have to choose, let us say there are n pixels, singularity. I have to worry about the singularity. When I take the r which is in the red font, when I take r to be one point in the pixel, I iterate over all the other pixels, all others are fine except the self pixel. There I have to do the singularity a little bit carefully, but it is not a problem because this Green's function we know has a integrable singularity. So, I get it in closed form, right. That is how I get my n by n system of equations, right. So, for solving the forward problem, no problem, okay. That is how I got my ER, right. So, this is the strategy that we used for the forward problem. Now, the reason I am spending so much time on recapping the forward problem is because the inverse problem is very similar in structure. Okay. So, let us look at what happens. So, the inverse scattering problem now. Back to our favorite equation, right. So, now when I want to solve it, I am going to make a few steps to get it into the language of linear algebra, right, because we do not solve it in continuous variables, we discretize it. So, this electric field inside the medium, I am going to call it u, okay. This chi r, I am going to call it x, and this incident electric field I am going to call it small e, okay. So, these are just column vectors. What is given to me is the scattered field, right. Now, this domain was capital D. Do I know the scattered field inside the domain or outside the domain? Outside the domain, obviously, because it is a non-invasive method. I cannot go inside the domain and measure field. So, I have this electric field that is measured only outside the domain. So, what is scattered field? Total minus incident, right. So, E minus EI is being recorded into a column vector S, okay. Of course, R should not belong to D. So, all of these are complex valued column vectors, okay, straightforward. This is my domain again. So, S is the ring of receivers and D is the domain of interest, okay. Now, this equation over here can take two avatars or two forms as you can see. First is when this R vector belongs to the domain, okay. So, this R over here, it is my choice where to set it. So, when I want to solve the forward problem, what do I do is I choose R to belong to this domain and I cycle over all the internal points, get n by n system. But let us see what happens in terms of linear algebra. So, let us just discretize this equation one by one term by one term. First term, electric field, what happens? It becomes u, okay. Just take this equation and symbol by symbol let us write it in the language of linear algebra. So, the first term is ER, which becomes u. Next is all of this k naught square integral g chi e. Chi is known in the forward problem, okay. So, we are going to call it x, okay, and then I have a u which is unknown and the right hand side is known, which is e, small e, okay. So, we call this what this is given the name is called the state equation, because it tells something about the state of the domain, okay. And if you give me x, I can solve for u, right. I can take u common from the left hand side, I will get identity minus g dx, which I have to invert and get the electric field, right. And this GD matrix, it has full rank. It is a square matrix n by n. Not only is it square, it also has full rank. Therefore, it is invertible. So, I minus GD is also invertible, right, and it has a unique solution, right. So, this all we know. Now, I can choose to move R out of D, right. So, that gives me the second equation. So, when R is outside D, okay. So, now what I will do is this EI term over here, I can move it to the left hand side, and this whole integral term over here, I will move it to the right hand side. So, E minus EI becomes S, right. E minus EI for all R belonging to capital S, this becomes the scattered field small s, okay. Then I have this whole integral over here, k naught squared g x e. Now, in this equation, when R is in capital S, the form of this is going to be different than what it was over here. Here R and R prime both belong to D. Here what happens is R belongs to S, but R prime continues to belong to D. So, the values of the matrix coefficients will obviously be different, the integrals will be different. So, I am going to call this a different matrix GS, just to distinguish it from this GD guy, there is a GS matrix, okay. And all of these, my chi has been replaced by the vector x, so it appears over there, and electric field is unknown u, yeah. So this is called the data equation because it is giving me a prediction of what my scattered field data should be, because that is what I measure. I only measure scattered field. I measure S. S is given to me. Okay. So GS into U into X is a kind of a prediction of what the scattered field should be if you give me U and X. Actually, I don't even know U and X, that's the problem. But if you were to give it to me, I can tell you, I can predict that this should be the scattered field.
So if you figure it out from R belong to D, you can actually substitute there and
If you could, we will see what is the problem in that, right. So now we can try to understand the whole problem of infinite solutions. Why are there infinite solutions? This GS matrix over here is actually underdetermined. Okay. So how many measurements will I make, right? So what will be the length of this S vector? How many ever measurements I have, that will be the length of S, right? If I have 10 measurements on the outside ring, then S has only 10 entries, only 10 points where E minus EI was measured, right? So if I call that, say, M measurements, that's your S. Now this domain over here, I want to determine it to a very high resolution, right. So I am going to chop it up into various such pixels over here. So some number n, right. So X is going to be of size n, and at each pixel over here, X is the unknown, but what is also there? U. The internal field over here, right, this E which is sitting inside the integral, that is also unknown, and that will be the number of unknown electric fields inside the medium is the same as the number of pixels that I have slashed this domain into, right. There will not be any difference. Wherever, if you look at this integral, wherever there is a chi term, there is a E term. So if you don't know chi, you also don't know E at that point. So the size of X and the size of U is identical. So X and U both are of size n. So in this equation, therefore GS is of what size? It is a matrix of size m cross n. So this is the reason why this is a underdetermined system of equations. And what is the problem with underdetermined system of equations? How many solutions from linear algebra we know? How many solutions does an underdetermined system have? Infinite solutions, right. So you can have a solution in the row space, but there are infinite null space components which can all give you exactly the same S. So this is the challenge of this problem. And
Can you explain again why S?
M is the number of measurements.
Okay, so what is the problem? Why can't you make them same?
Okay, very good. I was waiting for you to ask this question. Why can't I, if I want to, let's say, discretize and find out my permittivity in a 5 by 5 grid, let's say 25 unknowns, what prevents me from taking 25 measurements? Then I'll get a square system of equations. No problem. I have a lot of money. I can buy 100 receivers if I want. What's the problem? So actually you don't know enough to answer that question, so I'll give you the answer. There is another theorem in electromagnetics which we have not studied, which says that the fields, the degrees of freedom in this field on the boundary is fixed. Okay. In other words, the number of variables, the maximum number of variables required to characterize the field on this boundary is fixed, and it is fixed by something that is determined by the size of the object. So if the object size is fixed, the number of degrees of freedom available on the scattered field is also fixed. So if I put more sensors over there, I am not going to get more information. It is like oversampling a band limited field. Once I have satisfied Nyquist criteria, will I get more information by sampling finer and finer? No, right. So in fact, the theorem is a result which says that the scattered fields, right, I should write this. So scattered fields are spatially band limited. Okay, this is a very famous paper by an Italian person called Bucci.
So is there and m.
There is no relation between n and m. M, for example, the number of measurements, you can choose it to be at best how much? What is given to you by Nyquist rate. Okay. So, this theorem is telling you that the fields are spatially band limited.
So you will not get anything more, right?
You won't get anything more.
But then you still have the numbers same.
You have the number same, but your GS matrix now is rank deficient.
Oh.
Right? You will get a square matrix, but it's not full rank. And why is it not full rank? Because the sampling a signal beyond its Nyquist rate is what happens is that one row will be linearly one column will be linearly dependent on the other column because there is no new information. So this is the real reason why you cannot go any further over here. So what should you do? You should typically choose a number of receivers to be at the sampling limit so that you don't lose any information. But beyond that, can't help you. Right? So this is actually one of the reasons why this underground imaging is even more challenging, because you are losing important information below the ground. There is no way for you to recover it, right? So even though so that information is lost forever. Okay, and this band limit depends on basically what is the dimension over here. So if I want to image, head size, the head size is fixed. For this head size, the band limit is fixed. If I make the object bigger, then there is more information. But if for a given head, it's fixed.
But if the object size is very small,
Then
we can add more receivers.
If the object size is small, then the band limit is even smaller. So that means there is very little information. So you need very few receivers. No, see the amount of information is fixed by the size of the object. So size of the object gives you the maximum frequency, the spatial band limit, and that tells you how frequently I should sample. This is sampling in the space domain. Now if my object is very small, consider the smallest possibility 1 pixel wide, right? So how many unknowns are there? There are only 2 unknowns over there. So in principle, just 2 receivers, you will get everything. Just one sec. Is that clear? We are not dealing with rays. This is wave optics. So some or the other field will come to the receiver, right? There is no probability here. Once I send a wave, with probability 1 it's going to hit the object, with probability 1 it's going to get scattered, and with probability 1 it will be received. There is no, if it were a ray, then there is a chance will it hit or not, but this is where in the wave optics regime for sure.
So we know that m is the basis.
M is the number of measurements. Yeah. Why? Okay, good question. So if I know the band limit to be m, why should I not take m measurements only? M pixels, m unknowns. What resolution will suffer? Okay, I can solve the problem, but the resolution that I'll get will probably be coarse. You won't get a clear idea. You will get a fuzzy idea of what is there. You will get a fuzzy idea of what is in the domain. No, that's correct. So that is a strategy meant to get a good initial guess. That is correct, and that's a good idea. So you choose m equal to n, you can at least get a system which you can solve, and that's your good initial guess. Okay. Now I can give you some typical numbers in the microwave range. If I take a cross section of breast tissue or something, the number of receivers is usually no more than 10 to 20. So m is no more than 10 to 20. So n is the square of the number of pixels, right? N is the number of pixels. So if I even say 25 measurements, what is the best you could do? 5 cross 5, right? 5 cross 5. So if I have, let's say, an object which is 10 centimeters by 10 centimeters, I am getting information only 2 centimeters, but maybe I need more resolution than that. So it's workable but not good enough. So this is a challenge. Okay.